Hello everyone. I'm Hamza Haoui. I will be presenting our work, service-oriented modeling of mixed fleet systems in SysML v2. This work was done in cooperation between Tampere University and Johannes Kepler University, and it goes under the Mixed Fleet project funded by Business Finland. Starting from the problem description. Uh, Starting with definition of mixed fleet. Mixed fleet systems are systems that include multiple vehicles, autonomous and also semi-autonomous machines, and also human operators that need all to cooperate together in order to perform some business processes together. And our work is focused on modeling and programming those systems from domain experts. And when modeling those systems, complexity usually arises from having multiple stakeholders. And here, where we will have ambiguity in communication and the requirement. And also in mixed fleet systems, we have vehicles from different levels of autonomy. And also those vehicles are from different manufacturers. And the third reason is that, as we know, in cyber physical systems, we have long iteration cycles, and often the information got lost, and the implementation is almost different from the initial intent of the domain expert. One way to solve that was to enable domain experts themselves to program those machines directly without having to rely too much on on software professionals. And in order to explore that, we decided to go with model-based system engineering at the beginning, and to explore how SysML v2 can take part of the process. And we extracted the following three sub-research questions. First one, we start by checking if SysML v2 meets the service choreography requirements. And the second one, if are we able to extract reusable design patterns in order to have scalability and traceability of those artifacts. And the third research question is how can we connect those operational domain-specific constraints with requirements and verification. And in prior work last year, our colleagues in the same conference, they investigated if are we able to model those mixed fleet systems um, and keep them loosely coupled by separating who perform those services and the services themselves that need to be performed. And the goal from that is to keep our services our models loosely coupled, and we can reconfigure them easily independently from the actors. Uh, we break our modeling into 6 steps. First, we start by identifying business processes. Then we compose those business processes from services. And later we define also the events that goes between services and the data that takes part of those elements. And at the end, we describe the actors and we do the mapping of those choreographies. And in SysML v2, the equivalent would be that services are described through actions and events are action usages via the perform keyword, and processes are combination of services that need to be represented on an action succession flow, and the actors are described into parts where we can compose into them the actions that are the services that are represented through actions in SysML v2. For the modeling tools, we have been using SysIDE as our textual for the textual notation with SysML v2, and SysIDE helped us in order to scale our models and also to maintain consistency through the modeling spaces by offering syntax validation and also semantics highlighting. For the traceability conventions, we divided our modeling in four modeling spaces. This include action spaces for services and also structural elements for the actors, where requirements and constraints took part of the requirement space, and the verification in a runtime were defined on the verification space, where we have those verification cases. And in order to keep consistent our models consistent, we defined this traceability chain, where we can always compose elements from different semantic space together. For example, requirements can be composed in actions, and they can be verified once connected with the verification space. And also the actors described on structural requirements, we can compose actions into them. And in order to prove our modeling, we decided to go with one use case, which is the container movement use case, where we identified, in order to create the business process, we identified 6 services, which are inload, move, shuffle, and load of container, and also search and inspect, that are performed with UAVs. And for the requirements definition, we decided to use requirements and requirements definitions and usages in different way, where requirement definition is used to define those requirements in an abstract way, where we add attributes and also the constraints that take part of the requirements. And for the usage, we add our actors and stakeholders and subject, depending on the specific requirement that need to be satisfied. And for the verification cases, we have been using them in order to verify our behavior at a runtime, to check preconditions and post conditions. And in order to keep our modeling scalable and traceable, we have been using reusable modeling elements by using specialization and feature typing and composition across all our modeling spaces. For example, when it comes to requirements, we have this operational requirements that has few constraints, and those constraints can be propagated into other requirements, for example, for the movement and for the inspection or the search, where we inherit those constraints and properties, ensuring consistency across all our requirements. The same thing also for actions, where we can always define an operational action, and the other actions, which are our services, can inherit all what is composed into that, including requirements, constraints, and verification cases. And we have been using also feature typing and composition in order to integrate different semantical spaces together. And when it comes to integration across spaces, as we see here, we have this small example from our model, where we can see that a vehicle performing an action, for example, an AGV, can always have this container movement action that is composed, and it comes from the action space that satisfies some requirements defined in the requirement space, and it's on tight connection also with the verification case to verify the post conditions after the execution. And for the choreography modeling, we have been using normal action succession flow in SysML v2, where we add all the actors and the actions, and also the performing verification use cases that took part of the process. For example, here we can see that the vehicle movement test verification case will be performed after the container movement, and it returns a verdict for passing or fail, and based on that, the execution will continue. And for our modeling, during our modeling activities, we defined few modeling patterns in order to make those models more scalable and make the experience much more easier for domain experts. We identified 6 modeling patterns, starting from the specialization hierarchy, which is normal inheritance. For example, any vehicle can be specialized from the vehicle type. and also requirements composition, where we can compose requirements together, and constraints reuse, as explained before. We have been using the same constraints defined in the requirements in the verification cases in order to make sure that we are keeping consistent declarations in our system. And for the verification integration, we have been using the verification cases at a runtime in order to satisfy post conditions and preconditions, and the service participant specification, where we always at each requirement specify the subject and the stakeholders, actors, and items taking part of that specific requirement. And for the service choreographies, as shown before, we have been using action succession flow that will be mapped later to those service choreographies. For the result, we have been evaluating our models based on the 4 pillars of model-driven software engineering, starting from model completeness. We consider that we were able to do a full representation of the system, starting from the requirements to the actual representation of the system to the verification cases. So we have been able to model the full system. So we consider our models as complete. And for the modeling patterns, we extracted 6 modeling patterns to help domain experts to model those systems and guide the development process, avoiding deviation. And also for the language features, as we know, SysML v2 is built on top of kernel modeling language. So we got already this semantics that we can build on top of it and extend our SysML v2 library. And for the modeling tools, we had few difficulties when it comes to graphical modeling, but we consider that those limitations when it comes to tooling, they will be overcome over time since the language have been just recently finalized. And as a conclusions, to answer our research questions, if SysML v2 meets the service choreography requirements, so yes, we were able to identify elements to meet those service choreographies requirements defined earlier. And for the reusable patterns for scalability and traceability, we had identified few reusable patterns to help our domain experts. And we were able to close that loop by making all the elements connected and traceable starting from requirements. And for domain-specific constraints, we were able to use the same constraints in the verification cases and requirements in order to keep our modeling consistent through the keywords require and the assume, separating those constraints effectively. And for our future work, we are looking forward to integrate our models with the simulation, particularly Gazebo, in order to make our models the artifact itself, not just a representation of the system, and make them executable to help domain experts. And also we are thinking about exploring how AI-assisted modeling can take part of the process in order to make it more easier to domain experts. At the end, I want to thank Business Finland for their support, and also thanks for listening. And if anyone has any question, please, you can go ahead.